In this video, we are going to continue with the Laplace functions, and in particular, we will be looking at step functions because some of the most interesting elementary applications of the Laplace transformation occur in the solution of linear differential equations with discontinuous or impulse forcing functions. And just a note, unless specifically stated otherwise, all functions in this section is assumed to be piecewise continuous and of exponential order so that the Laplace transform exists for sufficiently large as S. We are going to start with the Heaviside function, also known as the unit step function, and it's associated with t greater than 0. When t is less than c, our unit step function will be equal to 0, and once we hit c, our unit step function will be equal to 1. And we can think of that as associating 1 with the value of on and 0 with the value of off. Then our unit step function, or our Heaviside function, represents a switch that is turned on at time t equals c. Here it's off, and then here it's on. And also, just a reminder, for a piecewise continuous function, the value at this discontinuity c is usually irrelevant, and we'll look at this a little more. The Laplace of the Heaviside function is given here. It's 1 over s e to the minus sc. Again, c is where the switch turns on. It ends up translations of functions is important because often we talk about the Laplace transform of a certain function, and we want to be able to take the Laplace transform if the function's just shifted over a bit. So we define this g of t is equal to 0 when t is less than 0, and it's equal to f t minus c. And this t minus c here plugged into f has the effect of, if this is our function f, shifting it over by c units in the positive t direction. And again, this g of t defines the function g of t as 0 before we hit c. So essentially, this graph here just gets shifted over. And we have these two theorems, which we will go over in the video, about translations. But I'm just going to read you for now the gist of the theorems. So if we translate a function t at a distance c, so we move it over c units in the positive t direction, that corresponds to multiplying the Laplace transform by e to the minus cs. So remember, this capital F is generally considered the Laplace transform of lowercase f. The other theorem we have is if we multiply a function by e of c of t, that results in a translation of the Laplace transform by a distance c in the positive s direction. We'll look at these more. One other thing I want to mention, and maybe I definitely should have mentioned this in my other video. We have this table of elementary Laplace transforms. So this is our function. This is the Laplace transform of those functions. When we take the inverse, we need to get our function in this form so we can find something. If we have the form of a over s squared plus a squared, we know the inverse Laplace is sine of at. And two things we often do are partial fractions and completing the square. So partial fractions, if you see your denominator can be factored, we often then will factor it and then apply partial fractions to it because we don't have anything with s4 minus a here, but we do have something with s squared plus, in this case, a would be equal to 1. Here, if we look at the denominator, s squared minus s minus 2, there's nothing of that form here, but we can factor this into s minus 2, s plus 1. And the partial fractions, of course, if you have 1 as the numerator, then you don't have to do anything. You just factor and separate out the two fractions. But if you have something on top, you'll have to use partial fractions to decompose it into a over s squared plus 1 plus b over s squared minus 1. Or in here, you would have a over s minus 2 plus b over s plus 1. And here you have an example of a denominator. You can't find that form here in this list. So since you cannot factor this cleanly, what you would need to do is completing the square so you can separate this out. And we will do examples of both of these, but I just wanted to point that out, that there are two techniques that often come up so that we can find things in this form of the Laplace transform, and that's partial fractions and completing the square. As I had mentioned, we are going to start by looking at the Heaviside function. And here's the definition of our Heaviside function, which is denoted u subscript c of t. It's equal to 0 when t is less than c, and 1 when t is greater than or equal to c. So you get this graph here. 0 up to c, and then it jumps up to 1 after you hit c. An example of using the Heaviside function, sketch the graph y equals h of t, where h of t is the Heaviside function u pi of t minus u 2 pi of t. To help me out with this, I start by looking at u pi of t, and by definition that's 0 for t less than pi, and 1 for t greater than or equal to pi, and this would be the graph. Similarly, I have the definition of u2 pi of t is 0 for t less than 2 pi, and 1 for t greater than or equal to 2 pi, and the graph over here. Now I can see what goes on when I have u of pi minus u of 2 pi. So here, from 0 to pi, both of these functions are equal to 0, so I'm still going to get 0. Between 0 and 2 pi, our u of pi is equal to 1, whereas our u of 2 pi is equal to 0. So I will get 1 for t between pi and 2 pi. Now, after 2 pi, our u pi of t is equal to 1, as well as u2 pi, so I get 0 for t greater than or equal to 2 pi, and this would be my graph. 0 from 0 to pi, and then 1 from pi to 2 pi, and then 0 greater than 2 pi. My next example is to sketch y equals f of t, this is my f of t here, and express f of t in terms of uc of t. I start by sketching my graph. For t going from 0 to 4, f of t is equal to 2. From 4 to 7, f is equal to 5. And from 7 to 9, f is equal to negative 1. And for t greater than 9, f of t is equal to 1. So I'm going to build up my function piece by piece. I'm going to start from t going from 0 to 4. Well, f of t is equal to 2. So that part was easy, but now I need to somehow incorporate the fact that once we get out to t equals 4, we go from f of t equals 2, and we jump up to f of t is equal to 5. So in other words, we're going to add 3 units. And I can express that as saying I start at 2, and then once we hit 4, we're going to add the unit step function, u of 4, and multiply that by 3. So now we have the correct answer for t equals 0 to 7, because this is equal to 0 when t goes from 0 to 4, so we have 2, but then once we hit t equals 4, this function here will equal 1 times 3, which is 3, and that will give us the 5 over here. Similarly, when we come out over here to t equals 7, well, now we're up at 5, but we need to go down to negative 1. So in other words, we need to go down 6 units, and we're going to multiply that at u7, because essentially this function stays 0 until we hit 7. And then finally, at t equals 9, we need to go up 2 units, so that's 2 u9 of t. And this is our final answer. And just to summarize, the u4, u7, and u9 are all equal to 0 when t is less than 4. So f of t is equal to 2 between 0 and 4. And then when we hit 4, these two are still equal to 0, but u4 becomes 1, and we multiply that by 3, so added to the 2, we have 5. Then when we hit 7, this becomes 1, this is still 0, so 1 times negative 6, we're going to subtract 6 from our 2 plus 3 times u4, so we get down to negative 1. And then finally, when we hit 9, all of these functions are turned on, and we get 2 plus 3 minus 6 plus 2. So that will get us back to 1. The next thing we need to do is determine the LaPlace transform of the Heaviside function. And I do this here. This is the answer here. But to see how that's done is I use the definition of the LaPlace transform. So the LaPlace transform of any function is the integral from 0 to infinity e to the minus st times our function. So here, u of c is equal to 0 when we're between 0 and c, so I put in the 0. And then between c and infinity, u of c is equal to 1. So this becomes 0, and I get the limit as a approaches infinity, c to a, e to the minus st, which is equal to minus 1 over s, limit as a approaches infinity, e to the minus st. So when we plug in a, this goes to 0, but then we get, when we plug in c, we get e to the minus sc. So this is our final answer, which I've written here. On our overview slide, we have that right here. The Laplace transform of our Heaviside function is 1 over s e to the minus sc. And just a note, the Laplace transform of u of 0, when we plug in 0 here, is just equal to 1 over s, which is the Laplace transform of 1. And this is true because u of 0 is equal to 1 for all t greater than or equal to 0. As I had mentioned before, when we look up inverse Laplace transforms, we often have different forms, and we need to know what happens when our function is of that form, but it's just shifted over. In other words, we have a function that might be the right shape for our Laplace, but it's shifted over from the table that we have. So what we need to do is be able to know what happens to the Laplace transform when we take a function and we shift it over. And so this is the function we're looking at. G of t takes f of t, it shifts it over c units. So if f looks like this, g of t will take this graph and move it over to the right c units, or c units in the positive t direction. And then since here f is not defined for t less than or equal to 0, this function will have to define it for t is greater than or equal to 0, and we just define it as 0. So this is our function g of t, which kind of shifts our graph over. And if we just want to capture this portion, we would let g of t is equal to uc of t, f of t minus c. If you've forgotten why this t minus c shifts your graph of f of t over c units to the right, I have this quick review for you. And I used the example of a parabola because most likely a long time ago in middle school or maybe high school, when you shifted graphs up or down or left or right, you were probably working with parabolas. So here is my original function, f of t equals t squared. And the question is, what do we need to do to shift this parabola over, let's say 2 units for this example, to the right? So f of t is equal to t squared, its vertex is at 0, 0. To shift to the right 2 units, what ends up happening is we need to shift the vertex over 2 units. In other words, we want the same value 0 for our y coordinate as we would have if it's 2 units. That means to get back to our original function, we would have to subtract 2. So let's look at this table, and I'll say that again looking at this table. Here I have the coordinate t, f of t, and the coordinate t, f of t minus 2. So we have this vertex at 0, 0. Now for this function here, if we want to have the value of f of t equal to 0 here, matched 2 units over, what we would need to do is subtract from the x coordinate, t minus 2, right? So by subtracting t minus 2 in the x coordinate, we get the same thing as if we had t equals 0, right? If c is equal to 2, then we have 0. In case this algebra here, to have the t minus c, the fact that it shifts it over c units to the right, is something you have forgotten because it was a long time ago, I have kind of this review for you here. It's very hand-wavy because I don't really want to make this video about this algebraic fact. But the idea, and I used a parabola because this is probably where you saw that in high school. It's when you were shifting your parabola up or down, left or right. And it turns out to shift to the right, you subtract c units, you subtract c from your independent variable. So here I have my parabola, f of t equals t squared with the vertex at 0, 0. If I want to shift this to the right, let's say c equals 2 units. We need the vertex now to be at 2, 0. And I also calculated f of t minus 2 is t squared minus 4t plus 4. So I could create this table. I have three values of t, 0, 1, and 2. I have the coordinate for t f of t, and then the coordinate for t f of t minus 2. At 0, we have 0, 0, and for f of t minus 2, we have 0, 4. For 1, we have 1, 1, and 1, 1, this intersection here. And for t equals 2, we have 2, 4, and 2, 0. So again, the idea is we want to focus, and this is again hand-wavy, if we want to focus on the vertex, we want to shift the vertex from 0, 0 to 2, 0. And the shift, it's the x-coordinate that changes. The y-coordinate we want to stay the same. And we want the y-coordinate at t equal to 0 to be the same as when t equals 2. In other words, we're going to subtract. To get the y-coordinate of 0, we need to take our function and subtract x minus 2 so that we get this f of t equals 0. So that sounded more complicated when I said it than when it was in my head. So the idea is for here, t equals 0, we want to shift that to t equals 2, but we want to have, so we're shifting over in the x direction, t equals 2, but we want this value for our blue function to be equal to the value of what our black function had at f of t equals 0. And to get f of t equals 0 over here, we would have to subtract 2 from our x-coordinate, right? So if we subtract 2 from our x-coordinate, that will give us the correct y-coordinate of 0, 0. Again, sort of hand-wavy because I didn't really want to make this video about shifting graphs, but hopefully this example, if you just take a look at it, will help convince you that it's possible, at least, that subtracting c from the x-coordinate will shift your graph over c units to the right. And then furthermore, since we shift it to the right, we need to define the function between 0 and c, and we just set that equal to 0. So in other words, our g of t is equal to uc of t, f of t minus c. And for this function, we can take the LaPlace transform. So the LaPlace transform of f of t, which we designate capital F of s, which is equal to the LaPlace transform of f of t, if it exists for s greater than a greater than 0, and if c is a positive constant, then the Laplace transform of this function here, uc of t, f of t of c, remember this is just the function f of t shifted to the right c units, is equal to e to the minus cs L of f of t. Or if we use the capital F as denoting our Laplace transform, that's e to the minus cs capital F of s. Once you start using this formula, it'll become second nature to you. Like you'll see this e to the minus cs, and you should associate e to the minus cs as a translation of your function by c units. And you should see this as a translation of your function f of t by c units. And I have that written here. The translation of f of t at a distance c in the positive t direction corresponds to the multiplication of your Laplace transform by e to the minus cs. Said another way, what happens to the Laplace transform when you take a function and you move the function over, you shift it to the right for a distance c? That means the Laplace transform then gets multiplied by e to the minus cs. The rest of the theorem, conversely, if f of t is the inverse Laplace transform of f of s, in other words, f of t is the inverse Laplace of f of s, then ut f of c of t minus c is equal to the inverse Laplace e to the minus cs f of s. So it's just sort of the same formula but written in terms of the inverse. I have this summarized here. Our Heaviside function, the Laplace transform of our Heaviside function, our translation of f of t by c units to the right, and then the theorem of what happens, essentially that here, if we translate our function f of t, if we translate f of t to the right, then we multiply the Laplace transform by e to the minus cs. Now we're ready to use this in a couple of examples. The first one is sketch the graph of f of t for t goes between 0 and 3, and then we want to find the Laplace transform. So f of t is equal to sine of t when t is between 0 and 4, and it's equal to sine of t plus cosine of t minus pi over 4 for t greater than or equal to 4. And here is why this theorem and this idea of translation is important. We know how to do the Laplace transform of cosine of t. And this here is simply a translation of cosine of t by pi over 4 units to the right. So that's where this is going to play in. Here is my graph. And again, as I mentioned, if f of t were not this function here, but if it were sine of t plus cosine of t, then I could use these Laplace transform formulas. If you look at your table, the Laplace of sine of at is equal to a over s squared plus a squared, and the Laplace transform of cosine of at is s over s squared plus a squared. So the Laplace transform of sine plus cosine, because it's linear, here a is equal to 1, so I have 1 over s squared plus 1. Here a is equal to 1, so I have plus s over s squared plus a squared. But as I alluded to before, is we have this step function, and also we have cosine t minus pi over 4. We don't have a formula for this form, but we can view this as a translation of our cosine function, and it's a translation to the right by pi over 4 units. So in other words, our function now is sine of t plus our translation of cosine of t minus pi over 4, and I'm going to multiply that by u of pi over 4, our step function, our Heaviside function, because I don't want this cosine t minus pi over 4 to come into play until t is greater than or equal to pi over 4. Now that I have my function written out in this form, I have the Laplace transform now of f of t is equal to the Laplace transform of sine of t plus, and from our theorem here, it says when we shift our function by pi over 4, where is this? Here. So again, our f of t is equal to cosine of t, but now we've shifted it by pi over 4. We have our Heaviside function and our minus pi over 4. That's equal to e to the minus cs, that's e to the minus pi over 4 times s, times the Laplace transform of f of t. And finally, I can use my Laplace transform formula for sine of t, my Laplace transform for cosine of t, and I get 1 over s squared plus 1 plus e to the minus pi over 4s times the Laplace transform of cosine t, s over s squared plus 1, since a is equal to 1. And I can add them together and put it in this form here. But this is my final answer. Either one is okay. And this theorem is captured here in the Laplace transform table, right? I have my f of t translated by c units, and that's e to the minus cf s times the Laplace of f of t. Not f of t minus c, but f of t. Our next example is to find the inverse Laplace transform of capital F of s, which is equal to 1 minus e to the minus 2t over s squared. The first thing to do is to break this apart into two fractions, since we don't have anything with an s squared on the bottom. And well, you could say a is equal to 0, but then you don't have something with something plus something else on top. But that's easy to take care of. Break it up into two fractions. So what I want is the inverse Laplace transform of 1 over s squared minus 1 over s squared times e to the minus 2s. By linearity, that's the inverse Laplace transform of 1 over s squared minus the inverse Laplace transform of 1 over s squared times e to the minus 2s. This one's easy. We can look it up really easily here. This here, remember I told you whenever you see this e to the minus 2s, when you're doing an inverse Laplace transform, you should think of this as having your function, whatever function gives you the Laplace transform of 1 minus s squared, as being shifted over by 2 units. As I had mentioned, the Laplace transform of 1 over s squared is easy. We could look at the table here, which I didn't put on this slide, which we could look up that Laplace transform of t to the n is equal to n factorial s raised to the n plus 1, which means the inverse Laplace of n factorial over s raised to the n plus 1 is equal to t to the n. If we let n equals 1, we get 1 over s squared. So the inverse of the Laplace transform of 1 over s squared is t to the 1, which is just t. Now when I look at the inverse Laplace transform of 1 over s squared plus e to the 2 minus s, which I have rewritten here, I should be looking at my theorem over here. So I have exactly this form. The inverse Laplace transform of e to the minus 2s, where c is equal to 2, and then we have a capital F of s. So our capital F of s is equal to 1 over s squared, and the capital F of s is the inverse Laplace transform of f of t. So if we want to find f of t, then we need the inverse Laplace of 1 minus s squared, which we found up here. Remember, inverse Laplace transform of 1 over s squared is equal to t. Looking at our formula for the inverse of e to the minus cs f of s, capital F of s, we need then to calculate little f of t minus c. So we said little f is equal to 2, c is equal to 2. So we need to calculate little f of t minus 2. So when we plug in t minus 2 into f of t, we get t minus 2. And the last thing we need to do now is multiply by uc of t. And in this case, c is equal to 2. So the inverse Laplace of 1 over s squared e to the minus 2s is u2 of t f of t minus 2, which is equal to u2 of t times t minus 2. As I had mentioned, this theorem is also captured in our table of Laplace transforms. So we have e to the minus cs f of s right here. So our inverse is going to be u, and here we take our c, which is 2 of t, and then f of t minus c. So u2 of t, and then f of t minus c. So we do need to know what, we do need to take f of s, get the inverse transform, which gives us f of t equals t, and then we plug in t minus c in for t, and we get t minus 2. So it'll give you the same answer. As you may have noticed, it is very easy to do this by table, but in case you don't have this table, someone doesn't give it to you, or someone asks you how do you derive this formula, you would essentially use this theorem here. So it's good to understand how we got this using the theorem, and it's convenient to know how we got this using the table. When you are a student trying to demonstrate your knowledge, both ways are good to know. So I'm going to look at this one more time. The inverse Laplace transform of 1 over s squared times e to the minus 2s. So I can find the inverse Laplace transform of 1 over 2s, and that's equal to f of t. And by the theorem, when I translate f by c in the positive direction, and again, that's f of t minus 2, then the Laplace transform of u2 of t, f of t minus 2, is equal to 1 over s squared e to the minus 2t. So the inverse Laplace becomes, just looking at this, the inverse Laplace of this is just this function here. And since f of t is equal to t, f of t minus 2 is equal to t minus 2, so I plug that in over here. We have one more theorem that's related to our previous one that says multiplication of f of t by e raised to the ct results in a translation of the Fourier transform by a distance c in the positive s direction. Formally, that is, if the Laplace transform of little f of t is equal to capital F of s is equal to the Laplace transform of f of t, exists for some s and a greater than 0, and c is a constant, then the Laplace transform of e to the ct f of t is equal to the Laplace transform shifted over by c. And then the converse, if f of t is equal to the Laplace transform of f of s, then e to the c f of t is just the inverse of this over here. And we'll do this example. G of s is equal to 1 over s squared minus 4s plus 5. Since there's nothing of the form of s squared minus 4s plus 5 in our inverse, because we're looking at the inverse, and the Laplace transforms, the first thing I'm going to do is try to factor this out. But when I factor, I get these complex roots, so I'm not going to do that. And instead, I'm going to complete this square. So I can do this as s minus 2 squared plus 1. And now I'm looking at the inverse transform of 1 over s minus 2 squared plus 1. And I'm going to look over here at my table, and I do have a b and a b squared. That's just b equals 1. And then I have my s minus a squared. So I do have something of this form, and that's the Laplace. This here is the Laplace transform of e to the at sine of bt. So just noting that Laplace transform of e to the at sine of bt is equal to b over s minus a squared plus b squared, and I just rewrote this here. So if I set a equals 2 and b equals 1, I get the inverse Laplace transform of 1 over s squared. 1 divided by s minus 2 squared plus 1 squared is e to the 2t sine of 2t. And this is a perfectly fine place to stop if all you're doing is solving this or answering this question here. However, we are going to take another look because we're going to ask, what if we didn't have this formula in our table here? So what if this formula wasn't available to us on a table? What would we do? Well, the answer is we would use the sine and cosine formulas over here, line 5 and 6, the Laplace transform of sine of at and the Laplace transform of cosine of at, and we would use this theorem to generate this formula here that I just crossed out. And we are going to start by looking at our function g of s, and we're going to look at the related function g of s is equal to 1 over s squared plus 1. So similar form, but in particular when we have g of s minus 2, when we plug it into here, we get exactly our problem, 1 over s minus 2 squared plus 1. And the advantage of this defining g of s as 1 over s squared plus 1 is now we can use our sine and cosine functions. In particular, we can look at the Laplace transform of sine of at and find that is a over s squared plus a squared. And this here is exactly what we have for our g of s, our modified g of s. So what we have so far is our Laplace transform of our modified g of s is equal to the Laplace transform of 1 over s squared plus 1, which means our inverse Laplace transform is going to be sine of at. But now we're going to use this part of our theorem that says that f of t multiplied by e to the ct results in a translation of the function, now we're looking at g of s, by a distance c in the positive s direction. So remember, we're looking at g of s minus 2. Rewriting what this theorem says in terms of our g of s, our capital G of s. In this case, okay, so our modified g of s is 1 over s squared. So the inverse Laplace transform of g of s minus 2. So in other words, here we have our transform, f of s, translated by a distance c. That's exactly this. Multiplies f of t, that is the inverse Laplace transform of sine of t, by e to the ct. So that's e, in this case, to the 2t. So this is how a second way of getting our answer. And it matches, fortunately, with the first way we used it, which was by table. So to summarize, we did this problem a second way, assuming that we did not have these table entries, this entry and this entry. So we couldn't just look it up by the table. The closest thing we had were the sine and cosines. So we viewed this function as this g of s function as being equal to a translation of this modified g of s function, 1 over s squared plus 1. So right, if we plug in s minus 2, then we get this old g of s. And the advantage of looking at this modified g of s is it allows us to use our Laplace transform of sine of at. So we could say the Laplace transform of sine of at is equal to this modified g of s. And then using our theorem, then we said that our ending capital F of s, our Laplace transform, this g of s here. Now, because we use g of s, this modified g of s, our original g of s is related by doing a translation. And if we translate the Fourier transform, then that's the same thing as multiplying our original function by e to the ct. So here's our original function, and then e to the ct. And this is what, and this theorem and this reasoning here is exactly how we can derive the formulas that I crossed out from our sine and cosine functions. So this is good for two reasons. One, you can see how this formula is derived, and two, someday you're going to get some function that doesn't fit neatly into any of these at all, and you're going to have to know how to think about it in terms of translation. So this is an example of how you can think of these in translations and modify your function so you can use this theorem and then get an answer. Our next example is define the Laplace transform of f of t is equal to u1 of t plus 2u3 of t minus 6u4 of t. You can just plug this in directly into our formula for the Laplace transform of the Heaviside function, but I also wanted to get a sense of what this function looked like. So u1 of t is equal to 0 up until 1, and then it switches to 1. Our u3 of t is equal to 0 and then it switches to 1 at t equals greater than or equal to 3, but we also multiply it by 2. So it's 2 times 1, which is 2, t greater than or equal to 3. And then our 6u4, so once we switch to t equals 4, we get 6. So I broke this up into the intervals. Between 0 and 1, we're at 0. And then at the switch t equals 1, we switch on to 1. And then as t goes to 3, we have our 1 plus our 2, which is 3. And then as we go to 4, we switch on this function as well. So we have our 3 plus our 6. And actually, this is a minus 6, so we get a minus 3. And then, as I said, you can actually just plug this into our Laplace transform. We get 1 over s e to the minus 1s, our 2 over s e to the minus 3s, and our minus 6 over s e to the minus 4s. This is our last problem. Find the inverse Laplace of 2s minus 1 e to the minus 2s over s squared minus 2s plus 2. And I just kind of rewrote this so that I could have it over this, so it looks nicer than this slash. So I have 2s minus 1 e to the minus 2s over s squared minus 2s plus 2, and we want the inverse Laplace transform of this function. And I also have this formula here. The inverse Laplace transform of e to the minus 2s f of s is equal to u2 f of t minus 2. And just a reminder, the Laplace transform of f of t, not f of t minus 2, but f of t, not shifted, is equal to capital F of s. This is standard notation, but I just wanted to remind you. And the reason why this is important, right, you can multiply this e minus 2s out, but also whenever you see this e to the minus at and you're looking for the inverse Laplace transform, you should think of pulling this out. And then you could do the inverse Laplace transform of what's remaining, the capital F of s. Because this e minus 2s simply will become the u2 of t, and then once you find little f of t, you're going to plug in t minus 2 into f. And this is a very common problem where you're looking for the inverse Laplace transform and you have this t to the minus or t to the at. You're going to pull that e to the at out, and you're going to focus on this capital F of s. And here we're focusing on our capital F of s, which is 2 times s minus 1 over s squared minus 2s plus 2. Here, since I cannot factor this out, I'm going to complete the square, and I get s minus 1 squared plus 1. Or I should say, since I can't factor without having complex numbers, I'm going to complete the square. To get the inverse Laplace transform of 2s minus 1, s minus 1 squared, first I'm going to pull out the 2, because it's linear, so I can do that. And I'll look at the inverse transform of s minus 1 squared plus 1, and that is right here. It's the Laplace transform of e to the at cosine of bt is equal to s minus a squared plus b squared. So that is the same Laplace transform we have, where a is equal to 1 and b is equal to 1. So the inverse Laplace transform is equal to 2 times e to the at, a is equal to 1, cosine of bt, where b is equal to 1. So I have my little f of t, again, which is the inverse Laplace transform of capital F of s. But what I have in my problem is I wanted the inverse Laplace transform of this times e to the minus 2s. And so in other words, it's right here from our theorem. So if we have this e to the minus cs times our f of s, then our inverse Laplace transform needs to be u of c times f of t minus c. So I'm going to start with f of t minus c. So I have our f of t, again, was 2 e to the t cosine of t. So f of t minus 2, plugging in t minus 2 for t, I get 2 e to the t minus 2 cosine of t minus 2. And then finally, our last step, our theorem says the Laplace transform of e to the minus cs f of s, that's e to the minus 2f s f of s, is equal to this here, u2 of t times f of t minus c. So this is our final answer. So in this video, we talked about the Heaviside function, which is equal to 0 when t is less than c, and then it switches to 1 once t is greater than or equal to c. So you can think of this as a switch, it's off, and then once it hits c, it turns on. We noted that the Laplace transform of the Heaviside function is equal to 1 over s, e to the minus sc. And then we looked at what happens when we shift a function by c units to the right. So the translation of f of t at a distance c in the positive direction corresponds to multiplying the Laplace transform by e to the minus cs, and that's what this theorem here says. A shift to the right by c units multiplies the Laplace transform of f of t by e to the minus cs. And then we had this other theorem that said multiplication by f of t by e of c results in a translation of the transform of the Laplace by a distance c in the positive s direction. So again, if we multiply our function f of t by e to the ct, the Laplace transform, so f of s, gets shifted over by c units to the right. And that's it for this video. Thank you for watching.